Today, inshallah, we will continue the topics of electrical transformer. This is slides part 3. The objectives of today's class is to understand the transformer maximum efficiency conditions and to learn the loading factor of transformer and its effect on the maximum efficiency and efficiency, to identify also the operation of distribution transformer, and to know how to calculate transformer all-day efficiency. And besides, also we can, if we have time, we will discuss the auto transformer. So let's start with the expression of all-day or energy efficiency. Now, Shabab, we have a power transformer which exists mainly in power stations for the transmission of electrical power. We need to step up the voltage before of transmitting this power to distribution. So the transformer of the power stations is mainly called power transformer. However, the definition of power transformer in general means that transformers that can transmit power, whatever the place of this transformer. Okay. For the distribution transformer, according to the place of the transformer itself at distribution, it has different design. And for the power station, all of time the transformer is designed to operate at maximum efficiency. However, this cannot be the case in distribution transformer because at loads you cannot control the loads of the customers. For that, you cannot control the operation of this transformer at maximum efficiency. For that, when we calculate the efficiency for distribution transformer, we can make another definition which is called energy efficiency or all-day efficiency. So simply, what's the meaning of energy or all-day efficiency? It's nothing but the energy consumption during a day. So the efficiency is the energy output consumed within 24 hours over the energy input over 24 hours, which is nothing but the input is the energy output plus losses over the 24 hours. And you know, we agreed together before, the losses of transformer can be classified to core loss, and this can be load independent because it depends on the supply voltage. Okay, and we can assume it's constant. However, the copper loss is considered load dependent because it depends on the current of the load. We have an example here. 10 kVA, 2200 to 22 or 220 volt, 60 hertz transformer has the following test data. This is the same example we solved before in order to identify the transformer parameter. However, here the requirements are different. First, find the efficiency at 75% of rated output and 0.6 power factor. So the load factor here is 0.75 of the rated, okay, and the power factor is given 0.6. So simply, for this part, we can get the efficiency. First, we need to calculate P out. P out is nothing but VI cosine phi, and VI, which is the total power or apparent power, which is given here 10 kVA, and we need here the 75% of this power. So we can say 0.75 multiplied by 10K multiplied by the power factor. So this is now the output power. For the core, we agreed before that core losses are independent of the load. So from the data here of the open circuit and short circuit test, we agreed also if we make the open circuit test at rated volt, so this power here is considered as the core loss. So we know the value of core loss here. And for the short circuit test, similarly, if we made the test at rated current, So the amount of power in short circuit test can represent the copper loss at rated or at full load. Okay, so we can say here that B core equals 100 watt and B copper equals short circuit power, which is 215 watt. If we apply in the relation of efficiency at 75%, so we can calculate using this relation. This is the efficient general relation for efficiency. Just apply 0.75 load factor multiplied by S by 0.6 power factor. And in the denominator, this is the core loss. And here is the rated copper loss, should be multiplied by X squared, because we agreed before that this value, the copper, is proportional to the square of load current. So we have to square the value of load factor. So X squared, which is 0.75 squared, multiplied by the rated short circuit copper loss, plus the output power. So for now, this is the efficiency, which is 95.3%. Secondly, it's required here to calculate the power output at maximum efficiency. And the value of maximum efficiency and the percent of full load at this maximum efficiency. So we need to calculate the output power, the maximum efficiency, and the percent of full load, which is the load factor, okay, the value of X. All of these are required here in this part. So from the definition of maximum power, and here in the problem, it's not stated that I need to calculate the maximum efficiency at certain power factor. So it means the global maximum efficiency operating point. So we have to consider that B core equal B copper and power factor equal unity. In order to calculate the maximum efficiency, we can start with the value of per unit loading, which is X, which is coming from this relation, square root of B core over B copper at full load. We have the values of B core and B copper at full load. Simply, we can calculate the value of per unit loading, which is here 0.68. Simply, we can apply now the value here in the equation of maximum efficiency. And you know, in maximum efficiency, we will remove the part of B copper by B core because it's equal here. So we can say P out at unity power factor. So we don't need to multiply by power factor now. So P out is just X multiplied by S rated divided by 2 B core, because B core and B copper are equal, plus X S rated again, which is the output power at unity power factor. Simply we can apply in this equation and give the efficiency at maximum power. طبعا يعني sure the value has to be higher than the previous calculated efficiency because this is maximum now. Any question, شباب? Is it clear? Okay, good. Here is another example about the energy efficiency. As you can see, this is a distribution transformer. We have 50 kVA transformer, 2400 240 volt, has a core loss of 200 watts at rated voltage. So this is mean this value will be constant. And copper loss equals 500 watt at full load. So this is considered also as the short circuit or full load power loss or copper loss. It has the following load cycle. Load cycle means the situation of transformer during the day. Load cycle here means we have the percent of load, this is the load factor, and the corresponding power factor for these load factors, and also the number of hours that the transformer is working during the day. As you can see, the summations here is 24 hours operation. 6 hours of them, the transformer is no loaded, okay, and the other or the remainder of 24-hour, the transformer is loaded with different loading factor and different power factor values. So the required here is to calculate the all-day efficiency of this transformer. Simply, شباب, we can calculate the power. Yani we can consider each part as a separate problem. Yani each part has certain loading factor with power factor for a certain period. So we can get the energy due to this period in a separate relation. And then we repeat this for many times, or we can collect them together. So we can say now, if we would like to calculate the energy due to this part, how we can calculate شباب the energy here? Who can say the relation of energy now, how we can calculate it using this data?
We find the power integrated on 6 hours.
Exactly. So what is the value of power now? We have load factor of 50%, and you know the apparent power is 50K. So what
since the power factor is 1, so real power هو apparent power.
Exactly. So we can say 50% multiplied by 50K multiplied by 1 by 6. This will give you the amount of energy for these 6 hours. Okay. Similarly, شباب, we can do the same for other periods. So we can collect now the overall energy during the day like that. Energy output over 24 hours equals 0.5, which was the part of the 6 hours that the load factor was 50%, multiplied by the rated kVA, multiplied by the number of hours, and the power factor here was unity. Similarly, we can do the same for other periods. Okay, and finally, we can get the amount of energy output during the 24 hours. So this is now represent the energy consumed per day. Now we need to calculate the losses during the 24 hours in order to calculate the efficiency. Like for the core loss, is it load dependent or independent, شباب? We said core loss depends only on the operating or applied voltage. So we can consider during the day that the core losses are equal. So simply, we have the value of core loss, which is 200 watts. So 0.2 kilowatt multiplied by the 24 hour will give you 4.8 kilowatt hour. Okay, one can ask here, we don't have operation during the first 6 hours. Why we consider 24 hours? يا شباب, why we consider تفضل. لا, the voice is not clear.
He said because the losses.
Okay, the losses. Why we consider core loss and not consider copper loss at this period?
Copper loss is load dependent.
So this means that core loss, even if the transformer is not supplying any load, there will be some losses. Is it right, شباب?
Yes, the core losses.
Yes.
Exactly. So we have to consider the core loss for the 24 hour. This is because the primary voltage is applied to the transformer, whatever the loading condition of the transformer. So we have core losses all of time. And you can feel that in the power supplies, which are based on transformer, you know, the chargers or adapters, small adapters. If you plug the adapter on the supply and remove the socket from the load, okay, and stay for several minutes or 1 hour, you will feel that the adapter is hot, even if there is no load. This is because there is internal core loss on the small transformer inside this adapter. Okay, so core loss exists all of time. Okay. So we can calculate the core loss as the power multiplied by 24 hours. Now this is the core loss or energy loss, 4.8 kilowatt hours. And similarly, we can calculate the copper loss for the different intervals as we made for the the output power, where here we have x squared multiplied by the power multiplied by the time. And if we return back again to the problem, you will find that the copper loss at rated is 500, which is 0.5 kilowatt. So we can say x squared multiplied by 0.5 kilowatt multiplied by the number of hours. Okay, and similarly for others. So x squared 0.75 squared multiplied by 0.5 kilowatt multiplied by 6 hours. And the same is also here for 3 hours and 3 hours. طبعا we don't need to multiply by power factor here. Here the copper loss is nothing but x squared B short circuit. So this is now the total copper consumed energy during the 24 hours. So easily we can now substitute in the equation of efficiency. You will find that the output power divided by the output power plus the total loss, core plus copper loss, and this will give you the amount or the energy efficiency, which is here 98.35. Any questions, Shabab, regarding this part? Is it clear? Okay. Now, let's start in another important transformer used in our life, which is autotransformer. Autotransformer means you have variable output supply. So you can find it in industry in different configurations. One of the configurations, can you see here, we have one winding, okay, N1, and we add a slide on a certain part of windings, like N2 for instance, and based on this connection now, this means that because N1 is greater than N2, this means that the output voltage will be a part of the input voltage, okay? Because this slide can move up and down, you can get different values of V2. And the maximum value of V2 here will be V1. So the output here by this connection is going to be varied between 0 and V1, just by changing the position of this point, which is made in practical life by a tappet changer, okay, or a slide moving on the top of the coil itself. For this kind of transformer, it gives a flexibility of having different values of volt. However, we don't have isolation between primary and secondary windings. Now it's not two winding transformer anymore. It's only one winding, and you use only one part of the this winding or one partial voltage of the input volt, okay? And you don't have isolation between primary or input volt and output volt, okay? So this is the one of the drawbacks of the auto transformer, okay? Because there is no isolation between input and output. And this was one of the main advantages of the two winding transformer. Simply regarding the relations, we can apply the same relations like the two winding transformer. For instance, if we started here, we have V1 and N1 turns. We have V2 with N2 turns. So simply we can say that V1 divided V2 equals N1 divided N2 equals A, which is the turns ratio. If we need to calculate the current and see if the turns ratio is available also with the current like the two winding transformer, simply we can drive it here from this circuit. So if we now get the ampere turns or MMF provided by the part of the windings, like the upper part between points A and B, and lower part between B and C. So for upper part A and B, which can be represented by number of turns N1 minus N2, we can say that the ampere turn equals N1 minus N2 multiplied by the current which is moving in this coil AB, which here is the value of I1. So we can say that F upper equals N1 minus N2 multiplied by I1. And simply, if you divide here the relation by N1, you can say that N1 can go here in the output of the brackets, and the relation will be 1 minus 1 divided turns ratio. So this is for the upper magnetomotive force. For the lower magnetomotive force for the part of coil BC or N2, we can make the same relation. So the MMF for this part equals N2 multiplied by the current which is moving out here. Sorry, which is moving inside the coil here. MMF for the coil itself means the number of turns multiplied by the current moving in the coil. So if you have I2 as output current, the current which is going to be moving here in this coil will be I2 minus I1. Okay, شباب, applying Kirchhoff current law here at this point, you will find that current equal I2 minus I1. So simply, we can say now F lower equal N2 multiplied by I2 minus I1. If we also divide by the turns ratio inside, you can find that replace N2 by N1 divide A, you can find the relation now N1 divide A multiplied by I2 minus I1. So we can now, if we make a balance for the ampere turn in this transformer, you can find that both of relations are equal. So we can make F upper equals F lower, and hence you can say 1 minus 1 divided A multiplied by N1 I1 equals N1 divided A multiplied by I2 minus I1. You can simplify this relation and you will get the same relation like the two-winding transformer. So in terms of relation, the auto transformer can be used with the same terms, with the same relations of the the two-winding transformer. So we have finally the relation of V1 divided V2 equal I2 divided I1 equals turns ratio. Here is a small example to understand the operation or how we can make auto transformer from two-winding transformer, and also comparing between them in terms of the performance and power. Simply, if you have transformer with the turns ratio 2000 over 200 volt, this is two-winding transformer, and the rating of this transformer is 100 kilovolt ampere. If we connected this transformer in such a way like that, this is here the 2000 turns, and here is the 200 volt turns, okay? So this is N1 and this is N2, and we add N2 on top of N1. So we added the low voltage coil on the top of high voltage coil now. So we can say now the transformer can step up the voltage from 2000 up to 2000 plus 200. So it can be used now as a step up transformer, but with a common coil. I mean, the coils here are physically connected. There is no physical isolation between primary and secondary anymore. What is required here? The portion AB, this portion, is a 200 volt as seen in the figure, and the portion BC is the 2000 volt. Compute the kVA rating as an auto transformer. If we would like now to calculate the kVA, we have first to see the relation between primary and secondary and the currents. As you can see, if you calculate the current for the part AB, this part, okay, we can say that the 100 kVA of the transformer divided by the 200 volt will give you 500 ampere. So this is for the two winding one. And also for the BC coil for the 2000 volt, the current of this coil is 50 ampere. However, in the connection now, if you place the 200 volt coil in the top of the 2000, this is going to make the primary current here equals the summation of the two currents, the 500 and the 50 ampere. So I low side now will be 550 amps, and the high side will be the same current of the 200 volt, because we cannot move in the coil itself higher than the rated value of the coil. So the 200 volt coil can support 500 amps, and this is the case here. And the high or the 2000 volt coil can support 50 amps, and this is also the case here. However, the input current here, because of the physical connection, will be the sum of the two currents. So for now, you have I of high side. We can say this is high side now because the voltage here is higher. I of high side is 500 amps and the volt is 2200. So we can say the apparent power here equals 500 times 2200. So you can see here the kilovolt ampere for the side of 2200 here, this is high side, equals 1100 kVA. Instead of 100 kVA, it's now 1100. If you can calculate also from the other side, which is the low side here, so 2000 multiplied by 550 amps, it will give you the same amount of kVA. So the conclusion now, if you use the two winding transformer as auto transformer, you can increase the overall power. Okay, شباب. And I think we can stop here now because of the quiz. Inshallah, next class we will continue discussing again the results of this example, and we will exclude some important notes regarding auto transformer. Okay, I will stop now the recording.